Now, as we are through with the circuit, such as the circuit which is containing of R, of L and of C in various combinations, now we want to understand that what is the term called the power factor, which is much widely used in the case of alternating currents, right? So the topic under discussion in this lecture will be the power factor. Now, the definition of this power factor, it may be described as this power factor is the ratio of the true power to the apparent power, right? So we can write this PF or power factor as the ratio of the true power in that circuit divided by the apparent power. In a circuit, there is a true power and apparent power. To understand it simply, we have devised a mechanism to understand this power factor or equate to this power factor. So this power factor is also represented as is equals to cos phi, where phi, actually this phi denotes the change of phase. So this phi, it is actually representing the change of phase. Now, as we have seen in various circuits like the LCR circuits, the LR circuit, the CR circuit, or simply inductive and capacitive or resistive circuit, we have seen in most of the cases the phi, there were various values of phi. Say for example, in a resistive circuit, the value of phi was simply equals to 0. Why? Because in that scenario we have seen the phasor diagram as such that the phasor I and the phasor E both were along the same line, right? But in, say, for LCR circuit, we have seen that the phasor I, that was lagging behind the phasor of E. So the phasor of E was actually leading, right? This was the case of LCR circuit. So we have to understand this phi first of all. Then we have to put the value of phi over here, and we have to take the operation of cosine, such as cos phi. So whatever the value we will get of cos phi, that will be equals to the power factor of that given particular circuit. Say for example, now we are taking the case of an LCR circuit, which means we have discussed it likewise, that over here this as base, on the base we had taken as R. Over here it was L omega minus 1 divided by C omega, and over here it was under root of R square plus 1 divided by it will be R square minus within bracket L omega minus 1 divided by C omega whole square, right? Now, as is this the case over here, if this is the angle, this angle is a phi, as we have discussed. Now this phi has to be that angle between this resistor and the total, like over here, this effective resistance, right? So in this circuit we can say this particular circuit, for this particular circuit, this is what? The LCR circuit. And in this LCR circuit, now we can say that the power factor is equals to cos phi. Now what will be the value of cos phi for this? This will be simply equals to R divided by the hypotenuse, the base divided by the hypotenuse. So this will simply be equal to R divided by under root of R square plus L omega minus 1 divided by C omega whole square. So this will be the case of the power factor, right? Now, taking the scenario of the power factor, there is one important term known as a Wattless current or the idle current. So we have to understand that what is a Wattless current or Wattless or idle current and why they are called as such. Wattless or idle current, it actually means that the current over here is not performing any work, which means that the power over here will be simply equals to like Wattless current. It means that the power needs to be zero. Now when the power will be zero? The power will always be zero whenever this power factor will simply be equals to zero. Why? Because if you can recollect about the LCR circuit, it was being devised that the power in the case of LCR circuit was equals to the value of the RMS or the RMS value or the virtual value of the alternating EMF multiplied by the RMS or the effective or the virtual value of the alternating current multiplied by cos phi. This was the expression for the power, right? And each and every scenario, like if you take it for LCR or LR or CR or L or R or C, it will be as such, right? Now let us see how. For example, over here, let us check that cos phi is equals to 0. Now if the cos phi is equals to 0, which means that R divided by this term will be equal to 0, which simply means that R is equals to 0. Now, if the R is simply equal to 0, then it means that there is no use of R in this LCR circuit. So this is not at all a LCR circuit now, right? But, say for example, we take two cases as, like the first case we take for purely inductive circuit. In the case of a purely inductive circuit, we have noticed that over there the alternating EMF was leading the alternating current by the phase change difference of pi by 2. So the change of phase of phi at this scenario was equals to pi by 2. So in this circumstances, we did observe that phi is equals to pi by 2. Because the alternating EMF was leading the alternating current. Now, whosoever leave that, just see that what is the change of phase, right? Over there I was denoted simply like as I naught sine omega t, and E was denoted as E naught sine of omega t plus pi by 2, right? And this pi by 2 over here is actually the phase change. So we can say that pi over here is equals to pi by 2. Now if this is the scenario, we can now say that the power factor in the situation of purely inductive circuit, or simply L as over here, we could write it as cos of pi by 2. Now what is the value of cos of pi by 2? The value of cos of pi by 2 is simply equals to 0, right? And if the value of cos of pi by 2 is simply equals to 0, we will observe that the power factor for over here in a purely inductive circuit will simply be equal to 0, right? Now let us take for the second instance over here as in a purely capacitive circuit. And if this is the scenario over here, we observe that the phi, this phi was again pi by 2. Now why this phi was pi by 2? Because in that scenario we did observe that the value of I was equals to I naught sine of omega t plus pi by 2, and the value of E was equals to E naught sine of omega t. So over here this is pi by 2. Leave that who is leading or who is lagging. Simply remember what is the change of phase between the alternating EMF and the alternating current, right? So we can write it as change of phase between alternating current and alternating EMF, right? So over here we can write that phi was equals to pi by 2, irrespective of who is lagging or who is leading. So again now we will find in this situation that the power factor in the case of a purely capacitive circuit will be equals to cos of phi, or where the phi is now replaced by the value of pi by 2, it will simply be equal to 0. So now we can see that the power factor of the purely capacitive circuit is also equals to 0. Now if this is the scenario, then obviously we have seen the power for a resistive circuit, a simple resistive circuit, that was not equal to 0. The total power in the entire time period from 0 to t, if you can like recollect, that was not 0 when we were considering only R. But when we were considering about only L or a purely inductive circuit, just remember it was equal to 0. This is only because the power factor is equals to 0. So over there, if you would multiply any EV or any IV with that cos phi that is equal to 0, the entire power will come out to be 0. Such was again the case for a purely capacitive circuit where the power factor is again 0. Now, whenever like the situations will arise, say for example a purely inductive circuit or a purely capacitive circuit, where the power factor comes out to be 0, we will tell that the current at that situation is wattless current or idle current, because at that point of time the current will actually do no work, right? So this is the scenario of the power factor and how we could relate it for understanding the wattless or the idle current. In the next lecture we will be discussing about the choke coil. Thank you. Now we shall be discussing the case of a choke coil. To understand the choke coil, first of all we need to understand the application of the choke coil, and thereby we need to understand that why choke coil is essential in an alternating current circuit. First of all, let us take not an alternating current, just a simple circuit which is having like a DC or a direct current. So this is a battery over here. Now over here there is a resistance, and over here there will be, say for example, a fluorescent tube. Now this will be the positive side and negative side of the battery, right? Obviously a current shall flow. It will pass through the resistor, go to the fluorescent lamp, and after that it will again come back in this way. Now, so for example, if we are going to omit this R, this resistance or this resistor of resistance R, then will it actually affect something? Yes, it will. Because if there is no resistor of resistance R, this current of I, which is a huge massive current, it will simply enter the fluorescent lamp and just to destroy or damage that fluorescent lamp. So in order to get the required amount of I or the current in the fluorescent lamp, we need to use a R or a resistor. Now come into the concepts of alternating current, where the main source of power supply is the AC. Over here we did take a resistance or a resistor of resistance R, and again a fluorescent lamp is connected to it. Now over here observe, again this I will flow the alternating current. Now this would be direct current and this would be the alternating current, because over here the main source of supply is the AC supply, and over here this was a battery. Now it will go through the resistor. After that the fluorescent lamp, the fluorescent lamp will get this I. Over here the Joule heating will happen, because how the fluorescent lamp or a bulb actually occurs. Like in a bulb over there, the filament is made up of tungsten, right? Like it could be of any material, right? The filament of this bulb, and this filament actually gets heated and starts to glow. Now, for example, the I goes over here, and there was no resistor of resistance R. Again, by the same principle, this massive alternating current could have damaged this fluorescent tube, right? So we need to put a resistor of resistance R in order so that our fluorescent lamp actually glows, or the fluorescent tubes actually glows, and also over here it does not get damaged. So we have devised successfully a mechanism so that the fluorescent tube actually glows and it does not get damaged, right? But there is a limitation. What limitation? Say for example, this was a DC circuit, the case 1. Right? And over here, this is the case 2, the AC circuit with a resistor of resistance, say R. Right? Now, what is the limitation with this? Why we are not, or why we shall not prefer this resistor? Because as per Joule's law of heating, the power that will be wasted, when I flows through R is equals to I square R T, the time through which it flows. So this is the limitation of our case 2, what we have discussed. So we are providing this alternating current from this AC supply, and we are sitting back in our chair saying the fluorescent tube to glow. But at the end of the month, whenever our electricity bill comes, we will see that actually we cannot pay. We cannot afford to pay it from our pocket. The bill, the amount on the bill will be so high. Right? Because the I that is flowing over here, that the power in this region that will be wasted will be equal to I square multiplied by RT, and R over here is the resistance. So we need to devise something so that this R becomes negligible. This R becomes negligible. Okay? No problem. We are going to keep this R over here of a minimum value, say of 1 ohm. Will that serve our need? No. Remember that we need to have something over here, a resistor or of a resistance, such that this fluorescent tube, now why this resistance is being used? So that our fluorescent tube does not get damaged. So if we are going to reduce this R in order to save our electricity bill, or in order to save our electric current in our household appliances, we are actually going to damage that appliances. So now we could understand that this scenario will basically not work at all. We have to devise such an instrument over here, or we have to keep something over here such that our device is not damaged, the fluorescent tubes does not get damaged, as well as this R is negligible, so that the power wasted over here, this power wasted should be very small. Okay. Experimentally, let us devise something in such a way of thick copper wire which is insulated, such that that copper wire is being made such that it gets a number of turns or wounds, right? So we may devise it as like over here, this is the AC supply, and over here we did connected the copper wire with a large number of turns. This is a thick copper wire, thick insulated copper wire with having a large number of turns, and over there in series we are connecting this fluorescent tube. Now over here, observe, that first of all, this is thick insulated copper wire. Now we have seen basically that copper is a good conductor next to silver, of course, because in many of the industrial appliances over there, in the industrial situations, we see that the wires, the electrical wires, are made up of silver, but the cost of silver is economically too high as compared to that of copper. So in this scenario, we are selecting a thick insulated copper wire. Now, if this copper wire is actually a good conductor of electricity, which means that the resistance of this copper is very negligible, right? Then only it could be a good conductor. So if this resistance is now negligible, we can say that as per the Joule's law of heating, the power that will be wasted will be very, very small. Because here R is negligible, so I square RT, it will be very small. Right? Okay, this is small, we have got no problem. We have also kept this small, but we are seeing that we are actually damaging our fluorescent tubes. So will it get damaged? No, it won't. Why? Because first of all, the power wasted, this, if we keep this as the third scenario, that AC circuit with L. Why L? Because if we are wounding this, this will simply look like an inductor, right? Now, we know in this third scenario over here, first of all, the power wasted, we have seen that it is very negligible. Why? Because the resistance of a copper wire, which is a very good conductor, is very negligible, which when equated as I square RT, the power wasted is very negligible. Now, say for example, we are going to understand in this case 3 about XL. What is XL? XL is the inductive reactance, as we have studied earlier. And what is the value of the inductive reactance? The value of the inductive reactance was equals to L omega, right? Now over here, see that this copper wire, which is insulated, it will be having an L, a self-inductance, a value of self-inductance. Why? Because whenever the current will start to flow like this, this will oppose it, as we have seen in the situation of self-inductance, right? So, like this current, which now will be flowing over here, will be actually lesser than what it was flowing over here, because it will oppose. This inductor will develop a self-inductance which will actually oppose the flow of this current. So now it is working just like a resistor, see, with this inductive reactance of equal to L omega. And due to this L omega, the I that will reach over here at this fluorescent tube will be not able to damage or destroy the fluorescent tube if we choose accordingly the number of turns and accordingly the thickness of this insulated copper wire. Because if we are going to put this L omega perfectly, then we will see that the I that is reaching over here will be lesser, and it will actually certainly light up this fluorescent tube, but is not going to damage it. So we have now successfully designed an architecture so as that the power wastage is also negligible, but also it is fulfilling our source. The power wastage is negligible, which means that our electricity bill will be in our reach. Secondly, it will be able to light up this fluorescent tube. And third, which is very important, it is not going to damage it. Right? So this is the scenario. Now, this thick insulated copper wire wound is actually known as the choke coil. So we may say that this particular region over here is the choke coil. Right? Now there are two situations over here, that the radio frequency and the audio frequency, right? So first of all, the two scenarios, the radio frequency, which means for high frequency. The term radio frequency, it indicates high frequency. For radio frequencies, we actually do use air core. And on the other hand, for audio frequencies, which mean actually for low frequencies, we use this same thick insulated copper wire, but with iron core, which means that in this scenario, this radio frequency, this is the scenario for this, and for this, for audio frequency, where we need low frequency, we are using it with iron core. So the device mechanism will be like this. This is a thick insulated copper wire, and over here we are actually inserting an iron core. Right? So this is the iron core which we are applying. So thus we have seen that what is the utility of a choke coil. The choke coil actually saves our electricity bill, which means that it actually lowers down the wastage of power. Secondly, it lights up the say for example the fluorescent tubes, the fluorescent lamps, etc. And also it helps this thing to not get damaged. Why? Because the current that will reach over here now will be lesser as compared to the current that was flowing in this region. Why? Because over here the self-inductance will occur, which will oppose to the flow of current, which is basically due to the XL, or the inductive reactance, which is denoted as L omega. Right? Thank you. Now, as we have seen in the case of like an inductor, there was an energy associated with an inductor, right? Now we shall be looking towards the case of the energy stored in a capacitor, right? Now, for example, if we check that this is a capacitor, the two parallel plates, and over here they are connected They are connected likewise. It could be connected like this. Now, say for example in this capacitor, the positive, like first of all, this is not charged, right? They are neutral. These two plates are neutral, right? Now, if they are neutral, first of all, we need to charge. How? Let's say for example, the positive charges we are transferring from one plate to the another, right? And if this is maintained, the difference between the potential difference between these two plates, if it is, say for example, V, in that scenario, the charges, the positive charges that would be actually like be transferred, we will get the ratio. For example, say Q is the amount of charge that is transferred. Amount of charge transferred. Right? So we will observe that in this scenario Q will be directly proportional to this V, and we will see that Q is equals to CV, where this C is the capacitance of these two plates. So we can say where C is equals to capacitance. Now, after this scenario, if we are going to transfer, say for example, a small amount of Q, like dQ, from the negative plate, then a work will be done. What will be the work done? We could say that the dW will be equals to, if this potential difference is being maintained as V, it will be multiplied by the amount of small charge that is being transferred, right? And over here we could write this V as Q divided by C, right? So let us replace it as 1 divided by C multiplied by Q dQ, right? Now if we are going to see this total amount of work done for the amount of charge, this GQ, from 0 to capital Q, the total amount of charge. This is the amount of charge that was transferred initially, and now Q is the total amount of charge transferred. Right? So, in that scenario, we need to integrate it from 0 to Q of dW, that is 1 divided by C of Q multiplied by dQ. Now, as we have seen in this scenario that C is basically a constant, so this will come outside. So this will be equals to 1 divided by C integration from 0 to Q of Q multiplied by dQ. Now integration of x dx is simply equals to x square divided by 2 from the laws of integration. So we can say it as 1 divided by 2c multiplied by the q square, which should be integrated from 0 to Q. The lower boundary is 0 and the upper boundary is Q, capital Q, the total amount of charge that is being transferred. So we can state it as Q square divided by 2C. Now the amount of work that is done is actually the energy that is stored in the capacitor, right? So we can say that this actually is the amount of energy that is being stored when the amount of charge Q is being totally transferred with the amount of the capacitance is equals to C, right? We can understand this scenario also graphically. Look and observe that over here we did mention that Q is directly proportional to V. So if on this axis we take it as Q, right? And if on this axis we take it as V, and over here we shall observe a straight line going likewise, for the given amount of Q, this is the value of capital Q, the total amount of charge transferred is equals to capital Q. We shall observe over here that there is an area which is bounded by this triangle. This one as the area, right? And as we know that if we are going to find out the area of this particular triangle which has been drawn according to the Q is directly proportional to V as of this line, we will find out the amount of energy. So this area will be equals to, this is a triangle, so the concept of half multiplied by the base and height will be, the base is C, it is from 0 to Q, so this will be over here Q, and this has attained a value of V, the voltage. So over here the height is V, we can write it as V. So it is equals to half QV. Now, what we can write V as? We can write V as Q divided by C, right? So we can write this area as equals to Q divided by 2 multiplied, the V will be written as Q divided by C. And as we know that this area, what we will find out will just be equal to the energy. So this energy in this situation will be equals to Q squared divided by 2C. So it is just the same as we have found it out theoretically, and like also when we can see the same is the case for graphically. Now, over here we could state as the energy stored in a capacitor is equals to Q square divided by 2C, and while we were discussing about the inductance or the self-inductance, we found out that the energy associated with an inductor during self-inductance is EL was equals to half multiplied by Li square, where L is the amount of, like this is the self-inductance L, and I is the amount of current that was flowing through that inductor. So this is the concept of energy stored in a capacitor and the energy stored in an inductor. This will be very helpful for us to understand in the subsequent lecture when we shall be discussing about the LC oscillation. Because so far we have only studied about either only resistor, either only inductor, or either only capacitor. After that, in series combination, resistor and inductor, and resistor and capacitor, and last, resistor, capacitor and inductor all at the same time. But we have not yet seen about only inductor and capacitor both in series. So, In the subsequent lecture, we shall be trying to understand the qualitative study of the LC oscillation, and also we shall be understanding that why is it called LC oscillation based on this concept, right? Thank you. Now, as we are through with the resonance, we understand that what resonance is. Now, we shall be discussing about the parallel resonance circuit. Initially, we have seen the resonance was in the series circuit of LCR. Now, let us see the parallel resonance circuit. So, first of all, let us draw the diagram that how this circuit will actually look like. Say, for example, this is the power supply of AC. This is the resistance over here, and in parallel to this resistor there is an inductor, and in parallel to this resistor and inductor there would be a capacitor. Now, as we know that what actually in series and in parallel means, from this given diagram we actually could deduce that if this is R, if this is L, of this L is the self-inductance of this inductor, and C be the capacitance of this capacitor. We know that if all this L, C, R and they are connected in parallel, then obviously whatever the voltage difference would be, say for example this is the voltage of LCR, the same voltage difference must apply to the R, L and C. As from current and electricity we know this fact. Now again, if the I is flowing as such over here, I, then at this particular point this I will get subdivided in two parts. First one, over here the I will start to flow. Say for example this is IR, and over here it will be say I2, and we can say it from the junction rule in current electricity that IR plus I2 will simply be equals to I. Now again when I2 will reach at this point, it will see again that there is a junction, it will again get subdivided as such. This will be IL, and over here this will be say the IC. This IC will come from this point. Over here IL will meet IC, and over here we will see the I2, and over here the IR will come, and now we will see the I. This is the basic representation of the parallel combination of LCR through this AC power supply. Now, there are certain terms which we need to understand right now. First of all, as we have understood about, like say for example, the admittance, okay, likewise, we will say that like admittance of this LCR, admittance which is of LCR, this will be simply equal to the reciprocal of like whatever the impedance of LCR is, or else we can denote it simply as under root of G square minus B square. Right? Now what is G and what is B? Simply G is known as conductance. Conductance is basically the reciprocal of R. Right? So we can say it as 1 by R is equals to G. Right? Now the thing comes is the susceptance. We could say it as susceptance. As we have seen reactance, the reciprocal of the reactance is known as susceptance. So the susceptance for L, this will be equals to 1 divided by XL will be equals to simply 1 divided by L omega. Right? And again, the susceptance for this capacitor is equals to 1 divided by the reactance of the capacitor. And what is the reactance of the capacitor? Xc is equals to 1 divided by C omega. So we will find it as 1 divided by, again 1 divided by C omega. And we know that the denominator of the denominator is simply equal to the numerator. So we can write this as C omega. Right? And as we know that the value of omega is equals to F, now we can plot some graph. Now say for example this susceptance over here, we could write it as BL and over here as BC. And basically B actually is a combination of BL and BC. This B over here, it is actually the combination of BL and BC. We need to understand that whatever the vector addition or subtraction will be over there for BL and BC, that will simply be B over here as B. Now, why are we going to find out this kind of, say, admittance, conductance, susceptance, etc.? First of all, if we wish to find out that what will be the effective resistance by this entire circuit, if we wish to find out, say for example the effective resistance offered by R, L and C is equals to 1. So we know that since this is in parallel, right, so the 1 by Y, or we could let us say take as the Z of LCR, right, where Z of LCR is what? Yes, the inductive, like the impedance of this LCR, right? So 1 by actually Z LCR, we know it, that this will be equals to, or else we can simply write it as Y, leave it as Y, because over here whatever the resistance that will be found out, let us take it as Y. So the 1 by Y, the reciprocal of Y, will simply be equals to 1 by R plus the actual resistance offered by this L will be XL, which is known as inductive reactance. So 1 divided by XL plus over here 1 divided by XC. Now observe what is 1 by R basically is. 1 by R is the conductance, or simply G. What is 1 divided by XL? It is VL or the susceptance L. 1 divided by XL. And what is 1 divided by XC? Simply susceptance of this capacitor of BC. Right? And what is basically 1 by Y? The 1 by Y is basically the impedance of the circuit over here in the denominator. And we know that the admittance is basically 1 divided by the impedance. So this 1 by Y over here is basically the admittance. So over here we can write that this admittance, we could do it likewise. Okay. So to understand this thing, we have now taken not the resistance or the reactance, because these terms are the conductance or the susceptance. So conductance means, like for example, the resistance is actually for in a copper wire, it will resist the flow of the electric current. But conductance on the other side means that how much could it allow the flow of the electric current, right? So that is the reason why we are simply taking now conductance, susceptance of L and C. Now let us see that how we can plot it with the frequency graph. Now as we are through with the series part, we could take a quick look over here. First of all, let us mark this R with the reading, that whatever will be 1 divided by R. So over here, if we are taking the frequency, and on this axis we are basically taking the admittance or conductance or susceptance, right? So 1 divided by R will actually mean a line somewhat like this. Now after that we found out, so this will be, say for example, G, which is equals to 1 divided by R. Now we are going to plot this L with the help of the blue ink. Now what is L? For the L, it is VL. So 1 divided by XL is equals to again 1 divided by L omega. So the 1 divided by L omega now will look like this. It will look like this. Right? This blue ink is for, say, BL, this blue line, right? Now we wish to find out the susceptance of this capacitor, which we will be marking it by the black line, the black ink. So the susceptance for the capacitor is simply equals to C omega. So this will look like this, right? So this is, say, BC. We can write this BC as C omega, and this BL as simply equals to 1 divided by L omega. BL equals to 1 divided by L omega, and BC equals to simply C omega. Now over here, observe that at this particular point, if we actually forget about this R for the time being, because in many areas it is only shown that the parallel resonance circuit is for L and C, but here we are discussing about all the LCR, so as to understand this very, very clearly. So if we do observe over here, this for L and this for C, right? Now whatever the B we shall be getting, that will be simply at this point, if we draw the projection where the curve BL and BC are intersecting, at this particular point, we will find out that this admittance for both the same is now same. They will cancel each other now. And if we draw this projection on the frequency axis, we will get a frequency that is the resonant frequency. Now, for this particular thing, we could see that if these two cancel each other, the only left out frequency is this area. Isn't it? Let me mark it likewise. Okay? So, this is the value of the actual admittance in this case. Because XL and XC actually they have cancelled out. Which means that this particular part seems like there is no resistance. There is, like in this part over here, we can see that this actually will happen like, if we could draw the diagram of this circuit now, this will look like this is the supply, this is the resistance, and over here we shall look like this. This is now open. It will seem like as if it is now open. Why? Because over here the admittance, whatever it will be, it will like it cancel out each other, right? So we can get it as this part as open circuit. As was in the case while we were discussing about, say, the series resonance circuit, this was the short circuit, which means that actually there were no resistance, and now it will seem that there is huge or infinite resistance. It will actually not help any of the current to flow through it, right? And if they are not going to make any of the current flow through it, it will seem that the current will come but cannot go, right? So this is an open circuit over here, because as we have seen that over here the resistance would be infinite and the admittance will be nearly like equals to 0. Now, from this we can understand that the resistance, that the actual effective resistance is over here, which means that at this particular frequency, at this particular FR or the resonant frequency, the admittance is so low. And if the admittance is so low, now if we draw a curve with frequency as on this axis and over here reactance on this axis, or reactance, or we may say it as impedances on this axis, then we will see if this admittance is lower, obviously the reactance or the impedance will be higher. Why? Because admittance is simply equals to 1 divided by the impedance, right? see that the admittance is equals to only, say for example, 0.2. So 1 divided by a huge value will only give us the numerical like value of 0.2, right? So over here we shall see that there will be a point somewhere over here. As this was low, this reactance will now be very high. Now observe very carefully. If this is the I, this is coming back, this is the resistor. Now what will happen? If the resistance becomes too high, over here we indicated that this one will be the potential difference across all R, L and C. So we will remain constant at this position, and from Ohm's law we know that basically V is equals to IR. Now over here, if V is constant, we may say that I now is inversely proportional to R. So the increase of R over here, keeping the V as constant, will decrease the I. Or in other words, the decrease of R over here will actually increase the I if V is taken as constant. Now, is the R increasing or decreasing in this scenario? The R is actually increasing. So, the current will decrease at this particular given FR. So, the curve will look somewhat like this, where we can say that this is the point of the resonant frequency, right? Now, say for example, from this entire diagram, we cancel out the R, right? If we cancel out the R, we will see that there is nothing. The current actually cannot flow, because this has already been an open circuit. And if this is an open circuit and if there is no R, there will be no line in between, there will be no connection from this point to this point, which means that the current cannot flow, right? At that point of time, if there is no R, this I graph will simply go to 0, right? Now, we can see from this scenario that at the resonant frequency, in the situation of parallel resonance circuit, the current is the minimum. So, we can say at FR, I is minimum. Or, if no R or resistor present in this circuit, this is the situation when the resistor is present. Now if there is no resistor present, then at FR simply I will be equals to 0, because this will be acting like a total open circuit now, right? So we can say that whatever the I that will be coming over here, going, that will be the minimum. So we can say this as I min, because I is the minimum. Now over here, if this is the frequency, resonant frequency at which the I is becoming minimum or at 0 given on the certain circumstances, why is it happening? This is happening because the admittance of this capacitance is actually cancelling out the admittance of this inductance. Now if we do the operation that BL over here we have seen is actually cancelling out BC, that means both are equal. And if both are equal, what is the value of BL? That is equal to 1 by XL or 1 by L omega, which implies 1 divided by L omega is equal to, what is the value of BC? or the susceptance of this capacitor. This will be C omega, so equals to C omega, or else we can find out that omega is equals to 1 divided by LC simply. And what is the value of omega? The value of omega is equals to 2 pi f. This will be omega square, right? Because omega square over here and C will come down, so omega square equal to 1 divided by LC, which implies that 2 pi f whole square is equals to, this will be Fr, because the resonant frequency at this point where BL is equals to BC will be equal to 1 divided by LC, and if we perform out, we will be getting the equation as F of R will be equals to 1 divided by 2 pi under root LC. So this is basically the resonant frequency at which the I is becoming the minimum or is getting to the point of zero when actually no resistance is being present. Otherwise, if the resistance is present over here, the I will be minimum, right? Now, as we have understood while discussing about the series resonance circuit, this parallel resonance circuit, they are known as the rejector circuits. As we have seen that the series resonance circuit where the acceptor circuit, this will be the rejector circuit, because over here we can actually find out the least value of the I. We can actually minimize the current, right? So this is all about the resonance circuits of the series and parallel. In the subsequent lectures, we shall be discussing about the most interesting part, that how could we devise some AC instruments like, say for example, the generator, motor, and many more. So watch out for more videos for live actions. Thank you. Now we shall be discussing about the DC generator or the direct current generator. Now previously, as we have seen the alternating current generator, we should be trying to look at what is the main difference between an AC generator and a DC generator, when we know that actually an EMF could only be induced within a given coil if the magnetic flux over there changes with respect to time. So, having the same principle, why are we saying it on a different names, right? Observe carefully, as it was the case with, say for example, an AC current. Likewise, there are two pole pieces of strong electromagnet, and over here it is the north pole, and over here this is the south pole of separate magnetic of, like, say, bar magnet or electromagnet or permanent magnet. Now in this scenario, we shall be getting within these pole pieces an uniform magnetic field, right? Say for this are the north and south pole, then obviously there shall be uniform magnetic field, which is better known as B. Now over here there is also an, like, now we we shall be discussing about the DC generator or the direct current generator. Now, as we could see that this kind of, like say for example, the diagrams we have also seen while we were discussing about the alternating current generator or the AC generator. And also we know that a current could be induced or an EMF is induced within a given coil if and only if the magnetic flux related to it changes with respect to time. So what made it named as the DC generator and the previous one as the AC generator or the alternating current generator? So after understanding the principle, the construction and the working, we shall also be understanding that why we are naming it on different terms, the DC generator and an AC generator. First of all, observe there are, say for example, two strong electromagnets. One electromagnet is over here and the other one is over here. This one is the diagram for, say example, when time t equals to 0, and this diagram is for time when t equals to, say for example, 2 seconds, right? So the construction is basically the same in both the scenarios. We shall be looking into the construction first. As over here there is the north pole and over here this is the south pole. So like as we have seen in the case of an alternating current generator, there would be north pole of this and south pole of another strong electromagnet. In this situation, we shall actually see that there is a strong electromagnetic, say for example, strong magnetic field, not electromagnetic, this is the magnetic field, right? And obviously this magnetic field will be joined from the north and will be going to the south, right? Now, as we can see, the same type of construction as we have seen in an alternating current generator. This is an armature, A, B, C, D. We have named various points so as to understand that how actually they are rotating about their axis. This dotted line from the center, it determines the axis. About this axis only we are going to rotate them likewise, right? Now this point D of the armature, it is basically connected rigidly with the ring 1 or R1. As we have seen in the case of an AC generator that the rings were basically totally circular. In this situation, this is not circular but instead is semicircular. We shall also be understanding that whether we could make this semicircular more smaller or not, but right now this ring 1 or R1, this is a semicircular one, and likewise the point C of the armature, it is connected to the R2 semicircular metal ring, and the R1 is basically connected to the brushes B1 and the R2 is connected to the brush B2. So likewise we could observe that B1 when connected with R1, it will act as one of the terminal, and on the contrary when B2 is connected to R2, it will act like a different other opposite like terminal. Okay. Now over here we could see that B1 and B2 are connected to each other via this resistance. Or say for example, we could devise as such that we could take this current or utilize this current if it is generated. We do not know that whether the current will generate or not, but yes, if it is generated, we could obviously use it to light the lamps in our house, right? Now, in this we can see A, D, R1, B1, R, B2, R2, C, B, and back to A. These are all connected, which means actually this has formed a circuit. But the armature area of ABCD only lies within this magnetic field, right? Now, say for example, we are going to rotate it likewise. So we shall see that if we are going to rotate it from this way to this one, so the BC will come in this direction, and the AD from inside the paper, it will make a loop to come like this. Say for example, this is BC and this is AD, the things will happen likewise. Right? And at a particular point of time, we will see that BC is actually obstructing the AD, as we have seen in the situation of an alternating current. Right? So in the case of an alternating current, we have seen an important thing over there, that first of all, that phi was equals to NBA cos theta, where theta was the angle between the normal of this plane of this armature to the angle made with the magnetic lines of force or the magnetic field. Okay. So initially, if we do think that BC is likewise, and now it has been rotated such as that it is completely obstructing the AD when you are looking from this point of view, right? At that point of time, the normal to the plane of this ABCD will actually lie along the same direction of B. Right? So in that scenario, we can say that theta is equals to 1, and if the theta is equals to 1, so the initially at this moment, the value of the phi or the magnetic flux will be equals to NBA, because we know that the cos of 0 is simply equals to 1. So we can state that initially phi will be equals to NBA, and after that, when we will be rotating this a bit like this, obviously the normal now will point in this direction, but the magnetic field will be the same as it was like this. So the magnetic field and the normal now is making a certain angle, say for example theta, right? This was, say for example, when BC was obstructing AD, at that point of time, this was, say, the magnetic field, and this was also the normal to the area of this plane of the armature ABCD. Now when we rotated it, actually this BC started looking like this, and the normal to the plane of this BC now will start looking like this, which means obviously now there is an angle between this N and B, which is phi, say for example theta, and this will occur after a time interval of t, because initially they were along the same direction, both N and B. Right now, after t seconds, they are seeming phi angle apart, right? So after time t, we shall notice phi t as equals to NBA cos, say for example over here theta t, because this is the angle. And as we have discussed that this theta t could be replaced by is equals to omega t, where omega is the angular velocity of the revolution or the rotation of this armature, right? So we can replace this theta t as omega t. So the expression what we shall be getting over here will be equals to nVA cos omega t, where n is the number of turns on this armature, B is the magnetic field, okay, and A is the area of this plane of this armature, and omega is the angular velocity by which it is being rotated, the frame is rotated or the armature is rotated, and t is that point of time or that instant of time what we are taking into observation. Now, as we know that due to this there will be an induced EMF, so the induced EMF will simply be equals to E will be equals to minus d by dt component of phi t, right? Over here it will seem as minus d by dt component of the phi t as nVA cos omega t, right? Now, as n, b and a all are constant, they would not be affected by their differentiation with respect to t. Only the thing that will be affected will be cos omega t. And as we know it from differentiation, we shall be able to find out that E will be equals to minus of minus omega nVA sine omega t, right? This negative and negative, they will cancel out to form the positive, so we can write that the induced EMF now is equals to E naught sine omega t, where obviously E naught will be equals to this omega nVA, where the E naught will be equals to omega nVA. Now closely observe that over here, if the E naught is equals to omega nVA, which means that E naught is the peak value of the alternating EMF, and thus the alternating current will also be having a peak value according to the only thing which is connected is the resistance. Now over here it may be noted that with the application of Fleming's right hand rule, we could be able to understand that in which direction basically the I will be going to get induced. Let us take the right hand. Let the thumb indicate the direction of the motion. Take BC. The BC, when it will be rotated, it will be coming like this. It means it is coming from back to front. I mean towards the reader. So my thumb of the right hand will point towards the reader. Right? Now, what will be this is for the motion. The index finger is representing the magnetic field. The magnetic field will be in this direction as is being mentioned over here, like this. So the pointing of, say, the middle finger will give us the direction of the current. Likewise, we will see that the direction of the current will be upwards. See over here, the current is going upwards. Likewise, if we do make the application of Fleming's right hand rule in this situation of the case in AD of the armature, we shall see that it is going backward, going away from the reader, the thumb being in this direction, right? Over here. This one will indicate the direction of the B or the magnetic field. Then our middle finger will give us the direction of the induced current in this direction. So now we have seen that over here the current flows like this and over here like this, so it will form likewise from C to B, from B to A, from A to D, then from D to R1, then from R1 to B1, then from B1 to R, then from R to B2, then from B2 to R2, and then from R2 to C. Right? Now, say for example, this has got rotated. We will now see this kind of thing. The BC after complete half revolution will come on this side and the AD will come on this side. Right? But it may be noted that the semicircular split rings or the semicircular metal split rings precisely will be all obviously changing because they are rigidly connected to the terminals. C is connected to R2, it means that C will always be connected to R2. C over here, C from over here came like this. So the thing or the split ring to which it will be connected will be R2. Likewise is the case for D and R1, the D and R1. Right? So if they change their direction likewise, will the current change? Say for example, this is an anti-clockwise or counterclockwise direction. Shall the current change like this in the clockwise? No. Because after this rotation, we will see AD coming in front and BC to go at the back. Again, by utilizing the Fleming's right hand rule, the motion in this direction, the magnetic field will be in this direction, means like this. Right? And then the middle finger will show us the direction of the current upwards. See now, this is upwards. Likewise is the case for when we will be saying and applying the Fleming's right hand rule, we shall see the current coming down from B to C. Now closely observe the difference, what it has been made. Previously the current was flowing from C to B and now it is flowing from B to C. Likewise, previously the current was flowing from A to D, now it is flowing from D to A. Another important factor is that previously the current was flowing from B to A, now it is flowing from A to B. Right? But the only thing is that the split rings will just be changed. The B1 and B2 will be there as it was. So now the current will start to flow from D to A, to B, to C, to R2, to B1, through R, to B2, then to R1, and then to D. Right? So we are saying that over here, the direction of the current is not changing. Right? And likewise, we could find out that if we are going to divide this expression by R, we shall be getting the expression for I as well. In that scenario, we shall be observing a very interesting fact. The interesting fact is that for every half cycle, it is seen that, say for example, the EMF or the current, it rises from its zero value, goes to the maximum value, and then falls back to its zero value. Right? Now when it will be possible? Observe this equation as E equals to E naught sine omega t. So whenever the omega t will simply be equals to 1, or sine omega t is simply equals to 1, or omega t is equals to pi by 2, then the maximum will be reached. But whenever this omega t is equals to 0, which means that this value of EMF or induced EMF or the induced current will be 0 likewise, right? As we know that for DC, where we can use only a resistor, the E and the I are in the same phase, right? The only part is that E will be higher, the amplitude will be higher, but the amplitude of I or the peak value of I will be a bit lower, right? So we can see this graph from this equation and from the working model. So initially we did observe that V1 when attached with R1, it was acting as a positive terminal. So in the first scenario we observed that V1 when attached to R1, it was acting as the positive terminal, and on the second we did observe that V1 when attached to R2, it is now acting as the positive terminal. And likewise B2R2 in the first case and B2R1 in the second case will act as a negative terminal, right? Thank you. Now we shall be looking about that how actually a transformer works, right? Now we shall be first of all understanding its the principle, then the construction, then working, and likewise we shall be understanding that what is, say, like a transformation ratio and how many types of transformer actually we can devise, and how actually we can transfer a current which is produced at one point for 2 miles apart to another region, right? Now, say for example, if we devise a transformer, the main and important part is that the designing should look in such a way that this particular thing is made up of iron, and obviously as you could see we are making this iron frame as an iron core but laminated. Why? Simply to minimize the effect of the eddy currents. Now over here we are providing, say for example, coils wound around, right? And on the other end also we are providing the coils wound around. Right? Now, these are coils which are actually like copper wires. They are made up of copper wires and obviously they are insulated. And if we are providing, say for example over here, we do connect it with an AC source. This coil is being connected to an AC supply source. So we shall observe that the current is being flowing within this coil, and the current shall be an alternating current. And as the moment we see that the current flows through it, we will be finding out that actually there is, like, say for example, the magnetic flux associated will change, which in turn will actually lead to the mutual induction in the other coil, right? And say for example, this coil may be used for transferring this amount of current to say like other household appliances, right? First of all, let us to term it as coil P and this one as coil S, where it indicates that P always will stand for the primary coil. Why are we saying it primary coil? Because over here actually the EMF or like the alternating EMF or the alternating energy is being passed, right? And this is the other one where actually we will see that the current or the EMF is induced because of the change of magnetic flux, right? So S over here means the secondary coil. Now observe closely that if we do say that, say for example, d by dt component of phi is the change of magnetic flux, change of magnetic flux per coil or per wound per number of turns, right? And let us check over here that NP will be equal to, it will be the number of turns in primary coil and NS is the number of turns in secondary coil, right? So first of all, seeing over here, we could find out the like EMF, the EP for this coil. So the EP will actually be equals to minus of the number of turns in the primary coil NP multiplied by the d by dt component of phi. And let us give it as the first equation. Now why have we multiplied NP? Because over here observe that d pi by dt is the change of magnetic flux per number of turns. So we have to multiply by the total number of turns which has been present over here. Okay? And similarly for this ES, we will get the expression as minus of now NS and again multiplied by d pi by dt, which is actually equal to the magnetic change of magnetic flux per number of turns. D by dt component of phi, let us give it as the second equation. Now let us perform the mathematical operation on these two equations, such as that we are dividing equation say 2 by 1. Then we shall be finding out that ES divided by EP will simply be equals to this negative will cancel out, and this one d pi by dt will also cancel out, leaving only NS divided by NP. Now this particular expression of ES divided by EP, which means that the EMF or the voltage along the secondary coil divided by the voltage that was along the primary coil, this particular ratio is known as the transformation ratio, right? So ES divided by EP is basically the transformation ratio. Now it may be noted that if over here this ES by EP, let us term it as equals to capital K. So K is now here the transformation ratio. Now if we find out that if the value of K is lesser than 1, which means that obviously NS will be lesser than NP, right? It means, first of all, let us take it as equals to 1 and greater than 1. Now we shall be discussing about K lesser than 1. If the K is lesser than 1, which means that the NS is lesser than NP, which means that number of turns in the secondary coil is obviously lesser than the number of turns in the primary coil, which again actually means is the voltage across this coil S is lesser than the voltage across this primary coil. So say for example the volt or the potential drop of this coil, that the voltage of this coil P is equals to, say for example, 200 volt, and if the K is less than 1, so ES must be lesser than 200, right? Now taking the scenario that when K is equals to 1, which means obviously that NS equals to NP. Likewise, we can write that NS is equals to NP, which obviously means that the ES, or the voltage across the secondary coil, is equals to voltage across the primary coil. So nothing is basically changing over here, right? And on the third scenario, if you do observe that if K is greater than 1, which means that the number of turns in the secondary now is basically greater than the number of turns in the primary coil, which indicates that NS is greater than NP. Which obviously means that now the potential drop or the voltage of this ES at the secondary coil is greater than that of the voltage of the primary coil, right? Now here comes the concept that if we actually get the voltage of the secondary coil lesser to that of the primary coil, we shall be saying it as a step down transformer, right? This one is the scenario for the step down transformer. So we can say this scenario as step down transformer, right? This is the meaning of transformer. And if we do observe that actually this voltage in the secondary coil is greater than the voltage of the primary coil, it means that it is the scenario for step up transformer, right? So over here for this scenario, this will be step up transformer. And this is basically a scenario for understanding, not for the transformer, right? Now, for long distance transformation, actually we use sometimes the concept of K equals to 1, but let us look at it at a later stage. Right now, we shall be dealing that for the step down transformer and for the step up transformer, how actually the construction should be. The iron wounding, like the iron core, will be as such laminated, right? This will be made of thick, like say copper insulated wire, like this is also made up of copper insulated wire. For the step down transformer, we shall see that NS is greater than NP, which means that the number of turns in the secondary will be greater than the number of turns, the number of turns in the secondary will be lesser than the number of turns in the primary coil, right? Now, there is a very important concept that it may be noted down. If number of turns in any coil is greater, that coil must be designed thinner, right? If we see that the number of turns in any coil is greater than that of the other, that particular coil over here, which we are saying that the NP is greater in the step down transformer, NP is greater, which means that this NP coil or this P coil will actually must be designed for a thinner copper wire. So we shall be observing that P, which is having the greater number of turns as compared to S, this will be made up of thin copper wires, but over here we shall be saying in S that it is made up of thick copper wires, right? Now, why is this so? We will be discussing it, but this concept is very, very essential while we are actually designing a transformer. Now, for the case of a step-up transformer, obviously, the number of turns over here shall be lesser, as we could see, than the number of turns in the secondary, which means that if it is lesser, we have to design this coil by, say, thick copper wires, right? Now, basically there are two types of transformers. The two types of transformer are, number one, the shell type transformer, and number two, the core type transformer. So, first of all, the core type transformer, and the other one is the shell type transformer, right? Now, whatever the design we are seeing over here, this is for a core type transformer. So this is a core type transformer. Now, how actually the shell type transformer looks like is that this basically looks something like this. Where actually the primary coil and the secondary coil are wound around, say for example, the same iron core. So this is the type of a shell type transformer. Actually, when we are using for industrial purposes, for large transformers, we do actually use the shell type transformer. Or instead, over there also, if we wish to use the core type transformer, we have to immerse this in a core, like in oil, right? Now, while oil is being used because the oil also acts as an electrical insulator, first of all, and secondly, it also acts as a coolant, right? which will actually lessen down the Joule's heating effect. Now, when we are discussing about the Joule's heating effect, it might strike our mind that if we are actually passing the electric current over here, then obviously there might be some heating, right? Yes, obviously there are heating, and yes, there are certain limitations of a transformer. Certain limitations of a transformer may be listed as limitations are as like, say for example, the first one we could state it as copper loss. Say for example, we are passing a high amount of current, say for example I, and yes, if the resistance of this, let's say copper wire is very high, then due to Joule's law of heating, the expression for I squared RT, if R is high, then the heating will be maximum. And if the heating increases, actually we are losing down our energy, which is needed to be transformed over here. Right? So, this may be reduced by the concept we know that actually the resistance of any particular coil is simply equals to rho multiplied by L divided by A. Where we know that rho is the resistivity of that particular material, and either we can decrease the number of L or we can increase A, where L means the length of the wire and A means the cross-sectional area of the wire. Now over here, observe that if we are going to increase this A, obviously this resistance shall decrease. If we are going to increase this A, what does it mean? It actually means that we are going to make the copper or the insulated copper wires thicker. So if we are making the insulated copper wires over here thicker, then obviously the resistance will be lower, which means that the heating effect or the Joule's heating effect will be lower, and thus we can actually reduce the copper loss. Now, the second loss, which is the iron loss. The iron loss means that actually when we are passing this kind of current and this kind of mutual induction is happening, observe that if current is being passed, there will be the eddy currents that will be generated. And that is the reason why we make the iron core as insulated, right? Or laminated, better to say. So, we actually devise the iron core as laminated. Now, the third is that the hysteresis loss. Actually, when we are providing this alternating current over here, this actually means that due to this current over here, it is simply unwanted or undesirably magnetizing and demagnetizing this iron core, right? So there will be a hysteresis loss over there. Now this could actually be like minimized with using not the iron core but to use an alloy of iron and silicon as the scope. So we may term it as alloy of iron and silicon, right? So these are basically the limitations of a step up or a step down transformer, whatever it may be. And these are the types of the transformer, the core type transformer and the shell type transformer, right? Now, the main thing is that why actually we need a transformer. Say for example, like if we go up on mountains, we may see over there that the waterfalls are present. And if waterfall is over there, we could actually think in our mind that if the water is falling down, and if we do devise over there some kind of thing such that like dynamo, or there is a kind of turbine which could be rotated by the falling water, so as the potential energy of the water above, when it comes down, it will be converted to the kinetic energy of the water, and after, at that time, the kinetic energy of the water will be actually used to rotate the turbine, which in turn electricity would be produced, right? Now if this electricity is being produced in the mountains, we could actually see that how cheaply we are actually generating electricity, which is obviously not possible to generate this kind of electricity in, say for example, urban areas or metro areas. Now, do you think that it will really be economical to like utilize or not to utilize that electrical energy which we were getting from the mountains? But it may be noted that from the mountain, say for example, this is the area of the mountain and this is say the area where it is city. But they are separated apart by, say for example, hundreds of miles. Okay, there actually comes the utility of the transformer. Because when, if not, we are using the transformer, then obviously we shall be observing that the current loss may happen. Say for example, we are taking only a straight wire which like takes the current along from this, say hundreds of miles. But that actually is impractical. It is not practical, right? Why? Because if we take this long wire, when the eye is flowing through the entire long wire, we shall obviously see that the Joule's law of heating is taking place, and after 100 miles when we are sending this eye, we shall actually be observing that we send some amounts 200, it reached only as 2, right? So, over here at this location, we are going to use this transformer. And at this location also, we are going to use one kind of transformer. But, over here, it shall be a step-up transformer, right? Which actually will increase, say, the EMF in the secondary coil. And at the area or the destination, we shall be using a step-down transformer, right? It shall look like this is step-up transformer we are utilizing, and we are sending this via lines, and over here we are utilizing, say, step-down transformer. So we can see that if we are going to utilize these transformers for like this kind of sending the current, okay, or sending the electricity what is being produced in the mountains, first of all, at the source we need a step-up transformer, and at this like the destination we need a step-down transformer. So this is all about the transformer. Thank you. Hello and welcome to today's physics lecture. Now, as we have seen in the DC generator, that over there we were looking into the graph of the EMF that was induced, and likewise the current which was induced. We could find over there, that the current that was induced was simply like this. Now, this is over here, I is being taken, and over here the time is being taken. Also, for example, we can say it as omega t, right? Now, the main part is that over there we were looking at the equation of E, and we did find out that it was in the form of a sinusoidal wave. And also we did found out that if we divide the E naught simply by R, we shall be getting the equation of I, right? Now, what happened to that was the current, even after the half revolution of the frame, the current was still unidirectional. But the current was an alternating one. So it may be noted, a very vital point, that in a DC generator, the current is an alternating current but an unidirectional one, and this type is known as pulsating unidirectional current. Now, this is due to half revolution, right? This is, say for example, then it would be for full revolution. So, if this is the scenario, the armature is revolving like this, only for this much amount of time it will show the curve like this, the I. And after again when it made the full revolution, which means that this one is coming again over here, it will show like this and like this. So starting from 0, we can observe that basically I, or this current, this pulsating unidirectional current, is making 0, or it is becoming 0 twice in every, say for example, revolution of the armature, right? And also it is noted that this current is actually fluctuating a lot. Now 0, then to maximum, then to 0 again, then again maximum, then to 0 again. This is fluctuating a lot. So, the main limitation of the DC generator is that there was no problem with any pulsating unidirectional current, but the behavior of this pulsating unidirectional current is that I, or the current induced, is very much fluctuating. So, the problem in hand is that the I, what we are getting from this direct current generator, is very, very fluctuating, because indeed it is a type of a pulsating unidirectional current. So, we devised a mechanism for its solution. We did now make the M, like the armature, as such that several coils are being connected in series separated by a certain distance. Say for example, if we do tell that this is a coil, we are putting it, say for like this, okay, you are taking the top view of a DC generator, so you will be seeing that this is like this, and in series to this, if we do connect another coil, so it will be like this, right? So for every revolution, we will see that whenever it revolutes half, this will also have the revolution of half, right? Say for example, for the sake of simplicity, we do take, say this is the first coil, say coil number 1, say for example this is coil number 3, say for example this is another coil number 2, and this is another coil, it is coil number 4. For the sake of simplicity, we are now taking over here that 4 coils are connected in series. So this will look like, if we are taking the top view, we can see it likewise. 1 coil, 2 coil, 3 coil, and say for example then the 4th coil, like this, right? So whenever there will be a rotation, we shall be seeing it likewise, okay? Now, the main advantage to use this kind of like arrangement is they all are separated by a certain degree or a certain angle. Say for example over here, if we are going to divide, we shall be finding out that all the angles do measure 45 degrees. Each and every angle between each and every coil there will be 45 degrees. 1 to 2, 2 to 3, 3 to 4, then 4 again to 1. Now in this direction, on the other end, you will find as 1 dash, which means the other end of this one. Over here you shall find it as 2 dash, 3 dash, and likewise 4 dash. Now, since in the scenario we were using like 1 only, as we have seen in the case of a DC generator, that we were actually using the coil as such that if we take the top view, we will see only 1 coil, not like these 4 coils. So, if we are taking the top view from over here, we will be seeing like this, but actually the thing will look like this when we are taking the front view, which means that the 2 ends, this end and this end, now are actually connected with the commutator or the commutator cylinder or the metal rings or the split rings, right? So for 1 coil we needed 2, like that split rings. So for 4 we needed how or which much? Simply equals to 8. Okay. So in this scenario we actually will need 8 commutator splits. Now, the main reason why we devise it as such is that When we see that this coil, say this 1 dash, is gaining the maximum value or the peak value of the current, just after that, after a few seconds or a few milliseconds, we observe that this coil 2 dash is now at that position for which the maximum current could be realized. Again, after it has passed that, it is seen that the 3 dash now takes the maximum value of the current. So, if we want to understand it graphically, say for example, we do take it as in this direction. We take, say for example, the EMF, and over here in this direction we check for the time. As we have seen that there was a graph like this, okay, but since we have drawn it E, obviously the value of E was greater, because I naught is basically E naught divided by R, where R is regarded as greater than 1. Okay, then only I naught will be lesser than E naught. Now, 1 and 1 dash represented by this blue line, we shall be drawing the curve of 1 and 1 dash with the help of the blue line. Now say for example, it is like this. It is starting from this point. Say for example this point. Let us check it until this. Now this is the one, and as we could see over here that it has attained the maximum values at these points. So this is the mark of E naught, where E naught is equals to omega NBA, right? Now, if this entire thing is under the influence of a magnetic field, then only we could show that there is an electromagnetic induction, and thus due to Fleming's right hand rule, the current is being induced within each one of the loop. Now, if we do rotate this entire arrangement in such a way that after this one has attained this maximum value, the 2 dash coil, now it will attain its maximum value. Say for example, 1 dash attained it at t equals to 0 second, and like 2 dash, this coil attains its maximum value as, say for example, in t equals to like 3 seconds, right? So we shall be indicating the 2 dash graph with the red ink. Something like this, right? Now the third, it will attain its maximum value again much later to that of 2, right? something like this. Now for 4,4' it will attain its maximum value again at a much more later point of time. So like this. So in this scenario we can observe that where it was only attaining, say for example, 0 twice in one revolution, it is attaining 0 at various numerous occasions within one revolution, right? But it may be noted that when, since this 1 and 3, they are separated by 90 degree, because the angle is this one 45 degree, this one will also be 45 degree, as each of the angle is equals to 45 degree. In that scenario, as 1 and 3 they are separated by 90 degree, we will see that when, say, let us check it as likewise high, low. When we will see that 1 is at high, we shall observe that 3 is at its low. Likewise, when we will see that 2 is at its high, the 4 which is separated by pi by 2, the 4 will be low. Again, when 3 will be high, 1 will be low, and again when 4 will be high, 2 will be low. Which means that this high is the maximum value, which we denote as E0, where E0 equals to omega nba, where omega is the angular velocity of the revolution of the frames, and the low obviously means 0. So now see that even if someone is attaining 0, 1 is at its high position, and the other 2 and 4, because 3 now is 0, if we take, okay, say for example, let us check something in this situation. Check it over here. See, here 1, this is 1, is high, this is 3, which is the low or the lowest or 0. But observe that 4 is having some value at this point. Likewise, this would be, this particular point, be the value of, due to this 2 dash coil. Right? So we will find out that at any point of time, at any instant, we will see that it is this value for first, for second, for third, and for fourth. So actually now adding up the instantaneous values for each and every frame of time, we will be getting the graph as like this. This is not a sine waveform, but obviously this is a pulsating, right? Now, as this pulsating was unidirectional current, likewise we shall also be finding out this pulsating as a unidirectional current, right? It should never come down to 0, because at any point of time we did not find out this terms going below 0, right? So it will also be a unidirectional current. But the main thing is that the EMF that will be over here, for example, the highest EMF obtained is E0, but the EMF that will be obtained in this scenario will be higher. say for example the E1 that has been obtained, obviously the E1 will always be higher than E0, or else it could be 0, or equal to E0. But nevertheless it will be happening that it will be lesser than E0, right? And another advantage is that actually with the help of this adding up of this instantaneous EMFs, right, we are going to get a much more stable current. And now, so for example, if we are not utilizing any Ford like this, and instead we are using 16 frames or say 16 coils. Now we are using 16 coils in series, then obviously it means that we have to use 32 commutator splits, right? And with the help of this, actually, the 16 coils are being used in a DC generator, and in that scenario, we will obtain a much more stable, like the EMF that is being induced over there. Say for example, it may be like this. If we draw the EMF versus time, we shall be getting a much more stable like this, right? Which is nearly very equal to a straight line. Okay, so this is the procedure how we can use actually a number of coil turns. They are attached in series, and like there is a certain angle of difference between each and every one, so that the other or the next actually attains the maximum just after the previous one has attained its maximum. And likewise we have the concept that how much actually commutator splits we need, or in how many parts we have to subdivide our commutator cylinder, and so we can actually overcome this limitation, and where we see that the I induced is very much fluctuating at the time of the make or at the time of the break. Actually the I is very high, and it could cause severe damage. So if we could make something like this which is nearly equal to a straight line, obviously we shall be saving our domestic appliances as well. Thank you. Now, as we have looked into the factors of a DC generator, now we shall be concentrating our study on the DC motor, which means the direct current motor. Now, the direct current motor or the DC motor is basically the converse of a DC generator. Let us look how. Over here we can see that there is a circuit first of all, and with the circuit there is a battery which is connected. So obviously this battery has got an EMF, which in turn, if this key is being closed, then obviously a current will start to flow. Now, as we have seen in the cases of like an AC generator or DC generator, over here we could say first of all that this current will flow like this over here, and after this the current flows. So for example the current flows, and after this the current will flow like this. As we know that this is B1 or the brush, which is obviously made up of carbon rod or metallic, and this is the split ring of the commutator cylinder. So for example, let us give it the name of S1, and this is the split ring, another split ring S2, and this one is obviously the brush 2 or the B2. Now closely observe that if the current flows like this, obviously if the key is closed now, then the current will flow like this from the battery, the positive terminal of this battery, to B1, then to S1, which obviously is connected to it, then it will flow in the circuit likewise. Let us give it the name as A, B, C, D. So the current basically will start to flow like this. In this direction, and after it has passed from B1, S1, A, B, C, D, then it will pass to S2, then to B2, and then if the key is closed, then up till the negative terminal of the battery. Right? Now, as we have seen that if there are placed two strong electromagnets facing the unlike poles, then obviously there shall be a magnetic field present. So the direction of the magnetic field in this scenario will be in this direction, right? And if the magnetic field is present, if the electric current is present, we know B and I is present. Now, say for example, if we take the help of the Fleming's left-hand rule, then obviously our forefinger, which will point towards this magnetic field, B, this is the this finger which is being over B, the middle finger, this will actually in the direction of the current. Say for example, we take this one as CD, we will see that this middle finger is over at CD, the direction of the current. This one, the index finger, it actually is directing the B or the magnetic field. Then the force will be indicated by the thumb of the left hand. So the force, as we could see, that this will come along towards the reader, and likewise in this scenario we shall see that B is in this direction, I is in this direction upward. So the thumb is indicating that it is going into the surface, right? So there will be force, but they will be acting not on the same line, obviously, which means that a torque will be generated or a moment of, say, deflecting couple, right? So as we know that we have derived the torque as equals to M cross B, or we know that the torque vector is basically the cross product of this M and B. We can write as the magnitude of torque will be equals to M B sine theta, and we know that M is basically equal to I A, and then this B sine theta, and this torque now, if there are n number of loops or n number of coils, right, it will be equals to N simply multiplied by N B I A sine theta, where obviously if we are taking this cross product, then theta is the angle between this normal to this area vector and B. So normal to A and B. Now say for example, this is the scenario when actually the plane of the coil is parallel to B, then obviously the normal to this area will be like this, or going inside the plane of the paper, right? Which obviously means that now this normal to this area is making 90 degree with B, or pi by 2. So if we replace now this theta as equals to pi by 2 in this scenario, we shall be getting the torque as equals to NBIA, right? So over here, now we could actually see that this A, B, C, D is now actually moving, or better to say revolving. What will happen is that we have seen that this is coming forward and this is going backward. So if they are like this, it will be going now like this. And so for example, we fasten up, say for a kind of belt, we fasten up a kind of belt over here, then actually we will see that this belt is rotating, right? If this is regarded as a shaft, then obviously the rotation of this belt wound around it will revolve, and it may revolve another shaft which is kept over here, right? Because it will go and turn like this, right? Now in this scenario we can actually see that we were providing which kind of energy? Electrical energy, and we actually got the mechanical energy as the output. So now we can say that the energy, that the electrical energy now has got transformed into the mechanical energy, because after this revolution, this S1 will actually come over here. It will be in contact with B2 now, and this S2 will be in contact with B1, but there will be no change in the direction of the current, right? Because simply it will be going like this. At that point of time, what will happen actually is this point A will be transferred over here, the D will be transferred over here, likewise over here it will be B, and over here it will be C, right, after half rotation. Now everything over here is fine, but if you do closely observe that we have read something in the cases of a generator. In the cases of the generator, we did actually see that if any coil like this is rotated, then it will generate itself a current within it, or to be precise, it will generate an EMF which will obviously oppose the cause that is changing it. So in the case of generator, we were not actually providing this current, but we were actually rotating this thing, right? Now after it has been connected, and after a while when this thing will see that it is rotating, it itself will generate a current within it. Let us take, for example, in which direction the current will be generated. Because if we wish to find out that, obviously we have to take the help of our right hand, as is said by the Fleming's right hand rule. Over here, the thumb, if the thumb indicates the direction of motion, obviously this was coming out, as we have seen, that this one CD, it was coming this way. So the motion like this, our index finger, it points towards the direction of the B, like this. Now the middle finger will actually give us the current which is induced. See, just in the opposite direction. So if this is, say for example, I, if this is I, if this is I, and if this is I, the opposite current that will be generated, let us say it by small I, will be in this direction. Again, a small I will be in this direction, a small I will be in this direction. So we can actually understand that if we were going to make a DC motor, when DC motor actually starts working, after that it has started revolving, the altered, like this I, this small I is also generated, but this is completely in the opposite direction, as is indicated by the opposite direction EMF indicated in the Lenz's law. Right? Now, obviously, if over here this was the EMF of the battery, say capital E, or we can state it as capital E is equals to EMF of the battery or the cell, then this current, this small I, which are now being generated, obviously will be due to a kind of the EMF that is induced due to the motion, right? That EMF is known as back EMF, and we indicate it by small e. So the small e is known as the back EMF induced. Right? So, applying the laws of current electricity, now we can say that the actual I that will be present, the effective I now that will be present within the circuit will be in this direction. Why? Because the I will be equals to capital E minus small e divided by R, where this capital E is the EMF of the battery, the small e basically is the back EMF which is being induced, and the small r is the resistance of the coil. Which is the coil? Say the ABCD. ABCD. Right? It will have a certain resistance, but the value of this small r is actually very less, and such that the value of E is also be lesser. Had it been that this small e is greater than capital E, then the current would have turned in this direction. Right? Now, say for example, if this is the expression at just the moment of the start, that when we have just closed the key, we will see over there that I at start will simply be equals to capital E divided by small r. Now, why is this, say for example, why this capital E, why this is not minus small e? Because over here we can see that at the time of the start there was no back EMF, right? And if there was no back EMF at that point of time, we will observe that this value of small r is basically very, very low, right? So if this r is very, very low, the I at the start will be very, very high. So we can state now that I at start will be very high. And if this I start is very high, then we can say that due to Joule's law of heating, by I square RT, actually this value of I could burn out this coil because so much heat will be generated, right? So now what do we need to do? Obviously, we need to increase the resistance of this coil, and say for example, if remarkably we increase the resistance of this coil, then do you really think that it is a practical idea? No. Because if we actually increase the resistance of this coil, the actual I that will be flowing through it in order to rotate this thing will come down. Why? Because we have seen in the expression the torque equals to NVIA, where it is directly proportional to I. Had we made the small r of the resistance of ABCD higher, then we shall be saying that I will be smaller, this torque would have been smaller, which actually means that there will be less movement, or the movement will be slower, right? Now, what to do? Okay, not a problem. We know that we want to, first of all, our problem in hand is that we want to increase this resistance, but we do not want it to get affected within this coil. So, if we want, say for example, to increase our resistance, say for example, this is the effective resistance, we want to increase with the small r, then obviously we need to add this capital R, which means where this capital R is actually basically very high, right? So at this point we need to connect a capital R in series, because we can see that this is in direct addition. So we need to add a capital R of a high resistance, obviously in series. Okay, not a problem. We are going to put the resistance over here. Say for example, if we do put a resistance over here, the value of this resistance, say for, is equals to capital R. Then, yes, our problem is sorted out. At that point, the I star will start acting like, if we add up this resistance, this I star will now look like capital E, because just at the moment of start there will be no back EMF. So this expression will look like capital E divided by small r plus capital R. So the effective resistance has increased. So this I at the start will be lower, and if it is lower, then obviously it will not burn out this circuit. Completed? No. This is not completed. Because again the same problem will persist, because after I start, when actually it will start to revolve, this I will start looking like capital E minus small e divided by small r plus capital R now. Which obviously means that the I at that point of time would be lesser than this I in hand. Again. So, we need to keep a person over here that at the point of the start give a resistance of 4 ohm. When actually it has moved a little, it removed 1 ohm, it will be 3 ohm now, so that this will actually start decreasing, right? After that it has revolved a bit more, it remove another ohm, there will be 2 ohm of this R, again 1 ohm and again 1 ohm, right? So in that scenario we will actually see that our problem will be sorted out, because after I start only, the problem in hand was that if the I start was much more higher, then it would burn out the circuit. But when we are actually trying to revolve it, we need an I higher, actually, indeed. So when we are starting, we are saying after that this induced EMF will just actually negate this capital E. So whatever the EMF we are getting as an effective will be lesser than this EMF. So obviously, if this is getting lesser, we can get this lesser step by step, right? So at the time of the, say for example, make of the circuit, and at the time of break of the circuit, we have to actually decrease this R step by step. This is the highest point and this is the lowest, right? So when we will see that it has started revolving in a full-fledged condition, we will see that this R over here has got its lowest value equals to 0. But at the time of the break, we know from Lenz's law again that an EMF will be generated in the direction of the EMF that was flowing, right? So in that scenario, we need to actually increase. So this is the highest point and this is the lowest point. So say for example, we are running this circuit, for example 10 seconds. In the very first second, we shall observe that the value of R is high, then it is decreasing. After 4 seconds it is 0, 5th second is 0, 6th second is 0. After 7th second again this R will start to increase, and at the 10th second it will be the highest, right? Now will there be anybody who will be actually taking out 1 ohm, 1 ohm, 1 ohm from this circuit or from this resistance? No. But yes, obviously we had devised, fortunately, a thing known as starter. This starter is basically a kind of resistance that when it sees that actually it is the I star, it will fix itself to its highest point. And after that, when it will see that it has started moving, it will like lower its value of R or the resistance. And again at the time of the break, it will simply increase the resistance of itself. So over here, we need to connect a starter, and the symbolic thing to show a starter is like this. So actually we can say that this arrangement is a starter itself. So now our problem in hand is solved. We are saying that this I star will not be higher, it will be getting reduced, or the I at the end will again get reduced. But at the same time, we will also see that when it is in the normal functioning mode or the intermediate time, this R will be equals to 0 and it will start acting like this, I equals to E minus E divided by R. So we can state that this phase is the intermediate phase. This phase is actually the phase at the start or the end or the make or break of the circuit, right? Thank you. Hello. Now today we will be looking about the paramagnetic substances. Now as we have seen in the previous lecture that how the diamagnetic substances actually are, and what are their properties. Now we shall be trying to concentrate about the properties of a paramagnetic substance. Now, the paramagnetic substance, first of all, is that the very first point of its property is that the nature of the paramagnetic substance is like if, say for example, a bar magnet is being kept and in its vicinity there is a paramagnetic substance, it is being attracted feebly. Contrast to the case where we have seen that in the diamagnetic substance they were repelled, but these are attracted feebly. So their nature is they get attracted feebly, right? Now the second point or the second characteristics is that, as we have seen in diamagnetic substances, their mu or their permeability was lesser than 1. Over here their permeability is greater than 1, but again slightly greater than 1. So the second characteristics could be stated as their permeability is greater than 1. Now, as we have seen in the diamagnetic substances that if they were suspended freely in an uniform magnetic field, they used to get aligned perpendicular to the direction of the magnetic field. The same is inverse in the case of a paramagnetic substance, which means that these paramagnetic substances, they actually align themselves along the direction of the magnetic field. So the third property is that, like if suspended freely, this paramagnetic substances aligns itself in the direction of the magnetic field or B, right? Now, as we know that like in the susceptibility of a diamagnetic substances, the susceptibility was lesser than 1. Obviously over here the susceptibility is like it is having a positive value as compared to that the diamagnetic substances, which was actually negative, right? So the susceptibility of a paramagnetic substances is basically having a positive value, but a very low positive value. So the fourth point may be stated as that the susceptibility is positive, but they are low, right? Now, as we have seen that like if a non-uniform magnetic field is present at that point of time, these paramagnetic substances tend to move from the weaker region to the stronger region of the magnetic fields. So it could be stated as the fifth point, they tend to move from the weaker to stronger regions of magnetic field. Obviously, this is a scenario when the magnetic field which is kept, this is a non-uniform magnetic field. Now, when it will be a uniform magnetic field, we know that it will align itself into the direction of what? The magnetic field. Now, for a paramagnetic substance, the same is the case of a diamagnetic substance. Like, as soon as we take off say for example, the magnetizing field, right, it loses their magnetization, which means that they do not have the capacity to retain, right? So it could be stated as, like the sixth point is that if the magnetizing field removed or taken off at that very same instance, they lose their magnetic property. The magnetic property, like they stop behaving like a magnet, right? Now, as we have seen that in diamagnetic substances, actually the magnetic lines of force, they tends to pass the region surrounding to that of the diamagnetic substance. But in the scenario of paramagnetic substances, actually the like B or the magnetic lines of force, they tend to pass through the substance. So the next point is the magnetic lines of force tends to pass through the substance. The next important characteristics of these paramagnetic substances is that, like when they are placed in a magnetic field, right, they develop within themselves a weak force of magnetization in the direction of B. So, they develop weak magnetization when placed in a magnetic field or B, right? Now say for example, like what are the examples of a paramagnetic substance? The examples of a paramagnetic substances are, say for example, aluminum, like chromium, like manganese, like oxygen, etc. So we can say the examples as aluminium, Cr, then like Mn, then O2, and it may be noted that the alkaline earth metals or like the alkalis are actually a kind of paramagnetic substances, right? Now, in this case of paramagnetic substances, there is a very important law which is known as Pierre Curie's law. Now let us see what is that. The Pierre Curie Law. Now, while actually in experimentation, Pierre Curie observed that the intensity, say for example, we write this as I, capital I, is equals to intensity of magnetization, right? And H stands for the strength of magnetic field. Now, it has been observed by Pierre Curie that if I is the intensity of magnetization and H is the strength of the magnetizing field, it has been observed that I was directly proportional to H by T, where T is the temperature. So we may say that the intensity of the magnetization is directly proportional to the strength of the magnetizing field and is inversely proportional to the temperature. So say for example, if the temperature is increased, obviously this I shall get reduced. And to change it into equality, we take the help of a constant C. So the expression looks like I is equals to C multiplied by H divided by T. Now, if we draw a graph of I versus this H divided by T, for small values of H divided by T, we shall observe that there is a linear curve for this I versus H by T. But say for example, if this H by T ratio increases above a certain limit, we shall see that the saturation has been developed in the curve, and hence we can say that actually the magnetic moments are aligned, right? Thank you. Hello and welcome to today's physics lecture in alternating current, wherein we shall be discussing some more facts about the AC generator. Now, as we have discussed in the DC generator, that there were various other coils which were used in series such that they are making a certain angle with each others. The angle between the coils, as we have seen in the previously about the DC, the limitations of a DC generator, we have devised that there were 4 coils such that they all were inclined to each other, the respective one, just the next one by 45 degree, right? Now, looking at that, it actually strikes our mind then why actually could we devise something in the AC generator? Yes, obviously we can devise those things, right? The first one we need to discuss is about the two-phase generator. And also we need to understand that what is a two-phase generator. As we have seen previously for, say for example, in the limitations of a DC generator, that depending on the number of the coils, there were brushes and like the rings attached to them. Likewise, in two-phase generator, there are only 2 coils, right? Say for example, this is one coil and the other coil is like that. But the main difference is that there should be 90 degree or pi by 2 angle of difference between them, right? And there will be separate brushes and separate like rings for each of these 2 coils, right? So first of all, it may be noted that in two-phase generator we are using 2 coils such that the angle between them is equals to pi by 2 on 90 degree, right? So obviously there will be coils, say for example coil 1 and coil 2, right? As we have seen the coils in an AC generator, like the coil was A, B, C, G, right? And it was rotating. So likewise, let us give the name of two coils as coil 1 and coil 2. So the EMF that would be generated by coil 1 may be represented as E1, and it will be simply, first of all, if we take it as E0 sine omega t. Then the other coil, which is actually placed at pi by 2 angle making with the coil 1, the EMF of that coil E2 will simply be equal to E0 sine of omega t plus minus pi by 2, right? It is the same as we have seen in the cases of the limitations of DC generator while we were discussing. So if there are two coils as such that they make an angle of pi by 2 like this, and this is rotating, right? In that scenario, we shall be seeing that the EMF which is being generated in the first coil, let us say for example take it as it equals to E0 sine of omega t, then obviously the EMF induced in the second coil will obviously be equal to E0 sine of omega t plus minus pi by 2. And this entire arrangement is basically known as the two-phase AC generator, right? Now let us come to the three-phase AC generator. Now we can actually, this is also AC generator. And now this is three-phase AC generator. Both are AC generators. Now as we could understand that in two-phase generator there were two coils. So in three-phase AC generator there will be three coils. How? Now, if this is the three coils, then what will be the angle of separation between them? Obviously, they will be aligned as such that they are making an homogeneous angle between them. Say, for example, these are the two coils being kept over here, right? And this is another coil being kept like this. So, this has to be the scenario for the three coils. And obviously, if there are three coils, then it will be making 120 degree or an angle of 2 pi by 3. Because we know that if the entire angle is equals to, say for example, 360 degree or 2 pi, then we have to divide this 2 pi in 3 equal angles. So it will be 2 pi by 3 or is equals to 120 degree. In that circumstances, let us say for example, we take the EMF of the first coil as equals to E0 sine omega t. This is the EMF induced in the first coil. In the second coil, the EMF that would be induced will equal to E0 sine of omega t plus, this was pi by 2 because the angle difference was pi by 2. Now it will be 2 pi by 3 because the angle difference will be equal to 2 pi by 3 from the first coil, right? So 2 pi by 3. But remember, there are three coils. So what will be the EMF that will be induced in the third coil? It will be represented as E3 and it will simply be equals to E0 sine of omega t. Now see over here, we have derived this expression of E2 in terms of E1, right? again we have derived this E2 in terms of E1 because E2 is making an angle of 2 pi by 3 with this E1. Now E3 will be making another angle of 2 pi by 3 with not E1 but with E2, right? So it will be omega t plus this 2 pi by 3, which is obviously the case for this E2, and again an angle of 2 pi by 3. So we can say basically that E3 will simply be equal to E0 sine omega t plus 2 pi by 3 plus 2 pi by 3 will give us 4 pi by 3. This 4 pi by 3 is actually the angle which this third coil is making with the first coil. Observe the angle difference is 120 degrees. This is 0, this is 120, and this is again plus 120, that is 240 degrees or 4 pi by 3. Right? Now, there actually, like we have seen, there was a simple AC generator. After that, now we are seeing there's a 2-phase AC generator and a 3-phase AC generator. Now, what are the advantages of this 3-phase AC generator over other systems, right? So now let us check them. The main advantages of this 3-phase AC generator over other systems of AC generator are, first of all, the output of 3-phase system is the maximum, right? Second, we can say as the output of this 3-phase system is basically consistent in nature or is constant. Right? And third, the last but not the least, is that whatever we have to devise in practical, in real life applications, that simply has to be economical, right? And this 3-phase AC generator is basically very, very economical in practical life. So we may say that the third main advantage of this is that the 3-phase system is practically economical. Now, as we have seen that there was only one coil and we could actually transmit that AC or that alternating current to the devices which we need, right, in our daily life applications. But, say for example, you can ask me that how can we transmit the AC which is actually being generated in a 3-phase AC generator? Obviously, we can transmit them, and we can transmit them in any of the two methods. The first method of transmission, 3-phase alternating current transmission, method. The first one to go is the star method. Now basically what a star method is and how we actually can do it. First of all, on utilizing the star method, it must be kept into mind that the loads on each and every of these three coils must be equal. It is very, very important, right? If it is not so, we cannot apply the star method. So I repeat it again. The three coils that are being used in order to produce this E1, E2 and E3 must be as such that the loads on these three coils must be same, right? Then only we can apply. Now, say for example, if we draw the diagram of a star method, say for example, this is one coil. This is another coil. And say for example, this is the third coil, right? Say for example, this is the one for which the E1 over here is there. This is coil 2. Say for example, the E2 is over here and this is coil 3 for which the E3 is over here, right? Let us give the name as this one is coil 1, this one is coil 2 and this one, say for example, as coil 3. Now also, each and every coil actually has got a common end, right? And at this common end, we can utilize, say for example, a neutral wire. This is neutral wire. Now why is this called neutral wire? And we can actually omit this neutral wire. How? Understand that whatever is given over here, E1, E2 and E3, when this all reaching at a point, then obviously whatever the amount of the E or the I or the current will simply be equal to the vector summation of the currents flowing through 1, 2 and 3 at that particular instance of time, this T. Right? This is, say for example, if T is equal to 2 seconds, then we have to put T equal to 2, T equal to 2 and again T equal to 2 over here. So at that particular moment, we will see that E1, E2 and E3 will actually see. This one is E1 equals to, say for example, take omega t as equals to 0, right, at the starting point. So we can clarify it with the illustration as such. Take omega t equal to 0. E1 will be equal to simply 0. This E2 will be E0 sine of 2 pi by 3 and E3 will be equal to E0 sine of 4 pi by 3. Now sine of 4 pi by 3 is basically equals to minus sine of 2 pi by 3. We know it from the laws of trigonometry. So we can see that actually E3 is cancelling out E2, right, at the point of this junction, right? And we can see over here that since omega t was equals to 0, E1 will be equal to 0. So actually the vector summation over at this point due to the coil 1, 2 and 3 will simply be equal to 0, right? But say for example, we take a line as such, another line from over here, and the third line as this one. Now we are trying for the transmission. Now this one, as it is coming out from the coil 1, this will be then termed as phase 1. It will be named as phase 1 line. This one as phase 3 line. And this one, since it is coming from the second coil, will be termed as phase 2 line. But remember that this line is actually not connected with this black line. This green line is not in no way being connected with this black line, right? This black and this green are separate entities. They are joined no way. So this will be termed as phase 2 line. Now there is a very important observation over here that, say for example, we have to transmit this AC. If we are transmitting this AC, taking as, say for example, the phase 1 line and the neutral wire, we can take it first. So we can actually transmit them as the phase 1 and the neutral. Second will be the phase 2 and the neutral, this line and this line. Third one is the phase 3, this line and the neutral line. We can transmit it. And the fourth is that, say for example, 1 and 2, only taking this phase 1 line and phase 2 line now. Fifth observation is we can take 2 and 3, or the phase 2 line and the phase 3 line only, and the sixth one as phase 1 line and phase 3 line. Right? In this scenario, we shall be observing that into this first 3, where we are actually taking the neutral line into account, the voltage difference between these two lines, that means the phase 1 line and the neutral line, will nearly be equal to 230 volts. Whereas if we are not taking this neutral line into account and we are only taking the phases line into account, we shall be observing that the voltage difference between any of the phase line will simply be equals to 400 volts, right? So we can now say that since this is 230 volt, this is lesser than this of 400 volt, we are going to utilize it in the purpose of, say, in the household applications. And this one, without taking into account this neutral wire, if we are going to have it, we can utilize it in the industrial purposes. So we can say it, this one as for household, and this one for, say, the industrial purposes. Right? Now we have seen this one as the first method of transmission, or the AC transmission from this 3-phase, the star method. Now, well, you may ask me that what will happen if the loads on these 3 coils are not the same? Then how can we do it? Yes, obviously we can do it by another method which is famously known as the delta method. So the second method is the delta method. In this, if the loads are not equal even, we can use it, right? And likewise, as this was the structure for the star method, now let us look into that what will be the structure for this delta method. Say for example, this is coil 1. this is coil 2. And this is the coil 3. Now also over here we will actually connecting all these 3 coils in the star method at a particular point. But we have done it likewise that the end of this any coil will be connected to the other coil. See, the coil number 1 is connected to the coil number 2 at this end and the coil number 3 at this end. This applies for all the coils, 1, 2 and 3. And we can actually draw it by, say for example, this is one line. This is another line. And this one as the other. Mind note also that there is no provision for any neutral line over here, right? So we can see that either we can take this or this lines for the transmission of AC, or this line and this line as the transmission of the alternating current, or else we can take this blue line and this red line for the transmission of this alternating current. So let us mark them as, for example, this terminal is A, this is B, and this is C. Right? So, likewise as we have done over here, we could say that the first option is that either we are taking A and B for the transmission, second as B and C, and the third one as, say, A and C. Right? Now, wherever we will be saying that either we are taking AB or BC or AC, like as we have seen that the differences was equal to 230 volt and the 400 volt, the potential drop like between this one neutral or 1, 2. Likewise, the potential drop between this A and B while transmitting, we will find it out nearly equals to 230 volts, right? And the same applies for BC and AC as well. So we can see over here that we will be getting the potential drop across any of the 2 lines as equals to 230 volts, right? So without, like, say for example over here the load N1 and the load N2 are not equal, but still then we can apply it in the form of the delta method in order to get the applications for this household. As we have seen the 230 volt, we were actually applying it on household applications. So likewise we can utilize this 230 volt for the household utilities or applications, right? So this is all about the 2 phases generator, 3 phases generator, the advantages of the 3 phases generator. Why? Because this is actually economical, the output is constant, the output is, say for example, the maximum over here in this system. And after that, actually it strikes our mind that how we could actually transmit the alternating currents. So we have seen the star method over here, and over here we have seen that actually there was a neutral wire, right? And the transmission between any of the phased wire and the neutral wire is equal to 230 volt, which we could apply it in the household applications. But for the industrial applications, we need a potential drop or voltage difference of 400 volts for nearly, and we could get it by applying any of the phase lines. Say for example, phase 1, phase 3, or phase 1, phase 2, or phase 2, phase 3. And after that, we have seen the delta method. Why? Because there's an important point in the star method that all these 3 wires or coils must be having the same load, but if it is not so, then we are going to utilize this delta method. Over here we can see that how we can actually transmit this AC by taking AB or AC or BC, and the potential drop between them will be equals to 230 volt. Right? Thank you. Hello and welcome to today's physics lecture, wherein we shall be discussing about the starter. Right? Now, if you could remember, while we were discussing about the DC motor, at that time we have confronted with a very special type of problem. Right? There was a limitation of the DC motor, as like we were providing an EMF so as to like a current will be flowed within the circuit, and as such there will be a force enacted which will actually make the rotation of the frame possible. Right? But at that time we did look on a very special point that due to this a back EMF will also come into resistance. Right? And at that particular point of time we get confronted with another special type of a problem, that if the back EMF at certain point of time is equals to 0, which means that the start, during the time of start or the break, the make or break of the circuit, the current that will be flowing will be very high. And if this is, it could actually burn up the circuit. And at that particular point of time, we were using this starter so as to increase the resistance, so that the current which flows at the time of the make or break of the circuit, the current is actually lesser. Right? But another problem was that while actually we were rotating, the rotation was actually being possible, it was being made in the DC motor. At that time, we never wanted that the amount of current to be lower. At that time, we wanted the amount of current to be the same as like what we were actually providing in the circuit. So, at that point of time, we actually did introduce the starter. Now, we shall be looking into the concepts of the working of a starter. As we could see over here in this diagram, these 2 points are being connected to the mains, right? So it means that the current might come like this and it will go like from over here to this, right? Let us mark it. Say for example, this is the point A and this is the point B. Now, when there is no current, obviously the soft iron piece which is kept over here and this recoil which is being turned or wound around, there will be no current flow, right? Which means that this won't act like an electromagnet. But as soon as the current starts to flow within this, it will start acting like a temporary magnet or an electromagnet, right? Now initially the soft iron rod actually is mounted and being like encircled by a spring, which obviously will allow the soft iron rod to rotate about an axis, right? Now, when the current is actually flowing at the time of the make of the circuit, what will happen is that the current will flow now, this will start acting like an electromagnet, and it will see a soft iron rod in its vicinity, so it will try to attract it. Obviously, as being a soft iron rod, it will get attracted towards the electromagnet. But as we know that this end of the electromagnet is kept fixed, right? And it could only revolve like this now. This head will be attracted towards this. So, at the time of the make of the circuit, we will see that this soft iron rod now will take this kind of position. This was the position when the system was turned off. But as soon as the current starts to flow, this electromagnet will now act as like a temporary magnet, and now it will attract the soft iron rod like this. Now closely also that the eye that is going through this, it will go through this arc, this red arc, this green arc, this black arc, and then to this soft iron rod, which is actually being glided or slided over this material, right? Which means that now the I will flow like this, then it will flow over here at this point and like this. So we can say that this is, say, point C. So the current will flow like A, C, over here, then like to B, right? So the total amount of resistance at this particular point of time, let us take it as case 1. And the effective resistance. In the case 1, which means actually during the make-off a circuit, the effective resistance, they all are connected in series, which means that it will be simply equals to R plus R plus R plus R. Let us say, for example, it is 4R. Right? After that, when actually the turning is going on, but feebly, right? Because as soon as you switch on, or let the current pass through the frame of, say, example, a DC motor, the DC motor will not start to revolve then and there, right? It will take some time. So, it will see that after over here, this rod again over here, this electromagnet, will start to act like a much more stronger temporary magnet, which in turn will deflect the soft iron rod like this. Right? Now if the current flows through over here, it will see that it will go through from A, then through electromagnet, then through this blue arc, then through this red arc, then through this like green arc, and then over here to D. Say for example, we mark it as D. Then over to this sliding material, on the material on which this soft iron rod is sliding over here, and then back to B. In this point of time, we will see that actually the current is not flowing through this black arc, which obviously means that in this is the case, say for example 2, if this is taken as case 1, in case 2, the current actually flows through R plus R plus R, only 3R. Right? Then, after this scenario, we will again see that the soft iron rod is now over in this position. Again, it will deflect it over here. Right? It will become much more stronger and it will deflect. So, say for example, in case 3, as you could see, the total effective resistance will only be this blue R, and this red R will be simply equals to 2R. In case 4, we shall see this like over here, and in case 5, so in case 4 it will be only R, and in case 5, we will actually see the effective resistance as 0. Now why? Because in case 5 we shall see the soft iron rod like this. So it will come from A to electromagnet, then over at this position say E, and then over on this material, and then to B. So there is no kind of, say, resistance over here, right? This situation actually occurs when the frame of the DC motor is revolving at its full speed, or the speed which is desirable, we want it. So this will be the full speed actually when we want the resistance to be 0, effective resistance to be 0. Now, if the strip resistance is 0, you may well ask me that in this point of time, the I will obviously burn up the circuit, but no. At this particular point of time, at this particular instant, the EMF, I mean the back EMF that will be generated will be enough to bring down the effective EMF on the DC motor, right? So like this we actually take. After that, during the break of the circuit, again we will see that this electromagnet will start losing its magnetic properties. So the iron rod will start to move again back to like this in its position. So again from full speed to case 4, then to 3, then to 2, and then over here at 1. So we can also represent this as a break. At the ultimate break of the circuit, the resistance again will be the greatest. And after that, obviously, when everything is over, this will again come back. Right? Now, to understand the situation, we have to understand another concept which is very, very important, known as the efficiency of a starter. This is about the working of the starter. Now, what about the efficiency of a starter? The efficiency of a starter, to go along with it, obviously, there are a few concepts which we must learn about. Is that the input power. What is the power that was input, right? Now the input power will obviously equal to the EMF that is being applied, the external EMF that is being applied, multiplied by the amount of current that is flowing in the circuit. So the input power will obviously be equals to EI, right? And we know that I is equals to the potential drop divided by the resistance. So we can say this I at any point of time is equals to this capital E minus, or is being subtracted by the back EMF, as we have seen in the case of a DC motor, divided by capital R. Right? From this equation, we could actually write it as that I equals to E minus small e divided by R. We can actually write it as the small e is equals to capital E minus IR. So, let us say, for example, give them the equation name. This is the first equation. This is, say, for example, the second equation. This is, say, for example, the third equation. Now we have to understand that what is the power, which is output, right? The output power is the one which is obviously the input power minus the power which is being wasted. Now, the power which will be wasted in this will simply be equal to the I square R, or due to the Joule's law of heating, right? So the power wasted could be written as I square R, right? Now the R what we are taking now, this capital R everywhere, is the whole amount of R we are talking about, right? So for example, we are saying in the second case, at that point of time, the R which is being taken into account is 3R, and at point 4, when we are talking about, the R is taken as simply equals to R, right? Let us give us as the fourth equation, and as we know that the output power will simply be equal to the input power, which means the equation 1 minus the power that is being wasted, that is the equation 4. So the output power will simply be equal to EI minus I square R. If you take out common I from over here, we shall observe this equation be turning out around E minus IR multiplied by I. Now from the third equation, if we do observe minutely, we will find that E minus IR, this quantity simply equals to small e or the back EMF. Right? So we can replace this expression by this small e or this back EMF. Let us give it as the fifth equation. Now the efficiency of a starter. For any machine, the efficiency will simply be equal to the output power divided by the input power. It is the ratio to the output power to the input power. Right? So, the efficiency will be stated as output power divided by the input power, and we denote it by eta, right? So the output power will be equals to small e multiplied by I divided by the input power will be equals to simply as capital E multiplied by I. You can see this I to be cancelled out, so this we can write this efficiency now. Equal to back EMF divided by this capital E or the applied EMF. So we can obviously see that the efficiency of any starter is basically equals to the ratio of the back EMF and the applied EMF. Now from this, if we to minutely observe that if ever at any point of time the back EMF becomes equal to the applied EMF, at that point of time the starter will be having the efficiency of 1, that is 100%. Right? Now let us do check about what will be the maximum power. Right? As we have seen over here, the maximum power, the output power is E multiplied by I, which obviously will be equal to E multiplied by this I. This I will get replaced by the second equation, that I over here is equals to capital E minus small e divided by R. Now, to finding out the maximum power, we have to take the concepts of the maxima and minima, right? So if we are going to differentiate this expression with respect to this back EMF, obviously we can find out a point which obviously can have the maximum power or the minimum power or the point of inflection, right? So over here, if we do actually differentiate, it will look like G by GDE of small e capital E divided by R minus small e square divided by R. From the laws of differentiation, we can do that the d by de of this A and B will simply equals to d by de of A minus d by de of B. So this will simply be over here capital E divided by R minus 2E divided by R. To find out the point where the maxima or the minimum will exist, we have to put this first order differentiation equated to 0. So this will be equals to 0. This equals to 0. This r could be taken out and it could be multiplied with 0 to get it simply equals to 0, which obviously will give us that capital E equals to twice of the small e, which in turn actually means that the back EMF is equals to applied EMF divided by 2, or the half of the applied EMF. If for half of the applied EMF, the back EMF becomes the value of half of the applied EMF, then obviously there shall exist a point of maxima or minima. Now, this was the first order differentiation, and if we differentiate again with respect to E, we shall find out the second order differentiation as equals to dE of capital E divided by R minus 2E by R. Over here, E and R in this expression, it is a constant, right? Which means that it will simply be equals to minus of 2 by divided by R. And obviously, can ever this R or resistance over here be a negative value? No, it cannot be. Which implies that the second order differentiation is having a negative value. And if the second order differentiation is having a negative value, we can say that over here at this point a maxima do exist. And if the maxima do exist at this point over here, we can say that when the back EMF will be the half of the applied EMF at that time, we will find out the maximum power, right? So this is the scenario for maximum power. Now look out, if ever this back EMF is equal to applied EMF divided by 2, now put it in this equation of efficiency, we shall find it out as the efficiency now will become 250%, right? So at this particular point of time, we shall find out that the efficiency of eta, it becomes as 50%, right? But in practical scenario, we never want this kind of maximum power. Why? Because the resistance in actual, the DC motor is very low, which means that the current that will be flowing through it will be very, very high, which actually could again burn up the circuit. So that is the reason why in practical sense or practically this condition is undesirable. So we never wish to get a circuit which will of the starter over where the efficiency of the starter will be equals to 50%, right? Thank you.